Welcome! In this session, we'll be tackling LeetCode problem number 171, titled Excel Sheet Column Number. This is a fascinating problem where we translate Excel-style column labels into their corresponding numeric values. Let's dive in and explore the solution step by step. The problem asks us to convert an Excel sheet column title, which is given as a string, into its corresponding column number. In Excel, column titles follow a specific pattern based on the English alphabet. For example, A corresponds to 1, B to 2, and so on, up to Z, which equals 26. After Z, the pattern continues with combinations of letters, such as AA representing 27, AB representing 28, and so forth. Essentially, the column titles follow a base 26 numeral system, where each letter represents a specific value. Take AB as an example. The first letter, A, contributes 26 raised to the power of 1, multiplied by its position in the alphabet, which is 1. The second letter, B, contributes 26 raised to the power of 0, multiplied by its position in the alphabet, which is 2. This structure allows us to calculate the column number for any given title systematically. Now, using the example of AB, the column number is calculated as 26, contributed by A, plus 2, contributed by B, giving a total of 28. The input for this problem is a single string, column title, which has a length between 1 and 7 characters. The string consists solely of uppercase English letters from A to Z. The output is an integer representing the column number corresponding to the given title. For instance, if the input string is A, the output will be 1, as it is the first letter of the alphabet. To elaborate, the column title A corresponds to the column number 1 because it is the first letter of the alphabet. Another example is the title AB, which translates to the number 28. This is calculated by taking the contribution of A, which is 26 raised to the power of 1, multiplied by 1, and adding the contribution of B, which is 26 raised to the power of 0, multiplied by 2. This gives us 26 plus 2, resulting in 28. Similarly, for the title ZY, we can calculate its corresponding column number step by step. For the column title ZY, the calculation breaks down as follows. The first letter, Z, contributes 26 raised to the power of 1, multiplied by 26, because Z is the 26th letter of the alphabet. This results in a value of 676. The second letter, Y, contributes 26 raised to the power of 0, multiplied by 25, as Y is the 25th letter of the alphabet. This gives 25. Adding these two contributions together, we get 676 plus 25, which equals 701. The constraints for this problem ensure that the length of column title is between 1 and 7 characters, and the column title is always a valid string of uppercase English letters. Additionally, the column number will always stay within the range of a 32-bit signed integer. Edge cases include scenarios like single-letter titles such as A or Z, which should return straightforward results like 1 and 26. For multiple-letter titles like AA or ZZ, calculations follow the base 26 numeral system. The maximum length of the title is 7 characters, which could represent a very large column number, such as FXSHRXW, but it will still remain within the 32-bit signed integer range. Another important boundary case to consider is the transition between titles, such as Z transitioning to AA, or AZ transitioning to BA. These transitions must be handled correctly to ensure the function provides accurate results for all valid inputs. To solve the problem of converting an Excel column title into its corresponding column number, we first considered different approaches. The brute force method provides a straightforward but inefficient way to calculate the column number. Here, we manually iterate through the string and determine the position of each character in the alphabet. For example, A maps to 1, B to 2, and so on. Using these values, we calculate the column number by applying a positional weight based on the string's length. However, this approach involves repeated calculations that make it unnecessarily complex. Its time complexity is n squared, which is inefficient for longer strings. On the other hand, an optimized approach leverages the fact that Excel column titles follow a base 26 numbering system. For instance, the column title AB can be broken down into two components. The first character A contributes 26 raised to the power of 1, multiplied by its value, which is 1, resulting in 26. The second character, B, contributes 26 raised to the power of 0 multiplied by its value, which is 2, resulting in 2. Adding these together gives us 26 plus 2, equaling 28. This insight forms the basis for a more efficient solution. This optimized solution can be thought of as converting a base 26 number into its decimal equivalent. We achieve this by traversing the string from left to right and maintaining a cumulative total for the column number. The weight of each character is adjusted as we progress through the string. To implement this, we start by initializing a variable called result to 0. Next, for each character in the string, we calculate its value using the formula ord plus 1, which gives the corresponding numeric value for the character. We then update the result by multiplying the current result by 26 and adding the newly calculated value. Once all characters are processed, the result contains the column number. The time complexity of this approach is O(n), where n is the length of the string, as each character is processed exactly once. The space complexity is O(1), since no additional data structures are used beyond a few variables. This method is chosen because it efficiently handles the problem requirements while maintaining simplicity. Another approach we evaluated is a recursive solution. This method processes the string one character at a time, starting with the leftmost character, and computes its contribution to the column number. The recursion continues with the remaining substring until no characters are left. The base case for the recursion is when the string is empty, at which point the function returns 0. Otherwise, the function calculates the value of the first character and recursively computes the result for the rest of the string. While this method is conceptually elegant and has a time complexity of O(n), it comes with a drawback. Its space complexity is O(n) as well, due to the recursion stack. For very large strings, this could lead to stack overflow errors, making the approach less practical for edge cases. As a result, despite its theoretical appeal, the recursive method was not chosen for this solution. The optimized base 26 conversion approach was ultimately selected as the best strategy. It directly maps to the problem's requirements and is the most efficient method available. The key insights here are that Excel column titles represent a base 26 numbering system, where each character contributes to the total based on its position and a corresponding positional weight, which is a power of 26. By iterating through the string and maintaining a running total, we calculate the column number in a single pass. This iterative approach avoids the potential pitfalls of recursion, such as stack overflow, and ensures that the solution is both time efficient and space efficient. The time complexity remains O(n), and the space complexity is O(1). This makes it robust enough to handle edge cases, such as very long strings, while adhering to the problem's requirements. By avoiding unnecessary complexity, this method provides a straightforward and reliable solution to the problem. In this problem, we're tasked with converting an Excel-style column title, like a Z or AA, into its corresponding column number. The key insight here is that Excel columns use a positional-based 26 numeral system, where each letter represents a digit, starting with it as 1 and Z is 26. For example, a single letter like A corresponds to 1, while Z corresponds to 26. When there are multiple letters, the value is calculated based on their positions and weights. For instance, AA represents 27 because the first A contributes 26 times its positional weight, and the second A adds 1. Similarly, AB translates to 28, as the first A contributes 26, and the B adds 2. To solve this problem, we'll break it into clear steps, starting with initializing our variables and then processing each character in the string to compute the column number. Now, to calculate the column number, we process each character in the string from left to right. For every character, we first convert it to its numeric value. Using the formula char_value equals ord, character, ord, A, plus 1, we can determine the value of each letter where A equals 1, B equals 2, and so on. Next, we multiply this value by its positional weight, which is determined by its base 26 position. For example, in a string of length n, the leftmost character contributes the most weight, and subsequent characters contribute decreasing weights. These weighted values are then added to a running total, stored in a variable called result. After all characters are processed, the final value of result represents the column number, which we return as the output. This approach works efficiently because it directly computes the result using a single loop and avoids unnecessary overhead. When implementing this algorithm, we also need to account for various edge cases. For instance, single-character strings like A or Z are straightforward, mapping directly to 1 and 26, respectively. For two-character strings, AA maps to 27, while AZ maps to 52. Similarly, for longer strings, AAA would map to 703. We must also handle potential invalid inputs, such as empty strings or non-alphabetic characters, either by returning 0 or throwing an error, depending on the problem constraints. On the optimization side, this algorithm is efficient because it processes each character directly without requiring additional data structures. By leveraging the ORD function, we efficiently convert letters to integers, and since we iterate through the string only once, the time complexity is O(n). The space complexity is O(1), because we only use a few variables for computation, regardless of the input size. The pseudocode for this solution is straightforward. We define a function that takes the column title as input. Inside the function, we initialize result to 0 and determine the length of the input string. We then loop through the string one character at a time. For each character, we calculate its numeric value using the formula ORD, title, I, ORD, A, plus 1. We then update the result by multiplying the current value of result by 26 and adding the new character's value. This ensures that each character's positional weight is correctly accounted for as we progress through the string. Once all characters are processed, we return the final value of result. In terms of complexity, the algorithm processes each character once, so the time complexity is O(n). Since no additional storage is used, the space complexity remains O(1), making this solution both time and space efficient. Let's walk through two concrete examples to solidify our understanding. For the input AB, we initialize result to 0. The first character has a value of 1, so result becomes 1 after processing it. The second character, B, has a value of 2. Multiplying the current result by 26 and adding 2 gives 28, which is the final output. Now, consider the input ZY. Starting with result equals 0, the first character, Z, contributes a value of 26, so result becomes 26. The second character, Y, has a value of 25. Multiplying 26 by 26 and adding 25 results in 701. This demonstrates how the algorithm computes the correct column number by iteratively processing each character and applying the base 26 positional system. The provided code efficiently solves the problem of converting an Excel column title to its corresponding column number. The method title to number is defined within a class solution, following LeetCode's convention. The function accepts a single parameter, column title, which is the string representing the Excel column title. Explanation of the code. 1. Initialization. We initialize a variable result to 0. This variable will accumulate the computed column number as we process each character in the input string. 2. Iterating through characters. Using a for loop, we iterate over each character in the input string column title from left to right. Each character corresponds to a base 26 digit in the column number calculation. 3. Character to number conversion. Inside the loop, we calculate the numerical value of the current character using ORD, char, ORD, A, plus 1. This maps it to 1, B to 2, Z to 26. 4. Updating the result. We update result using the formula result equals result asterisk 26 plus value. This multiplies the current accumulated result by 26, shifting it one place to the left in base 26, and adds the numerical value of the current character. 5. Return the result. After processing all characters, the computed column number is stored in result, which we return as the final output. Example walkthrough. For input column title equals AB. Start with result equals 0. Process A, result equals 0 asterisk 26 plus 1 equals 1. Process B, result is equal to 1 times 26 plus 2 equals 28. Return 28. Time complexity. The time complexity is O(n), where n is the length of the input string column title, as we process each character once. The space complexity is O1, as no additional data structures are used. This implementation is concise, efficient, and handles all valid inputs as described in the problem's constraints. This is the Java implementation of LeetCode problem number 171, Excel sheet column number. The logic mirrors the Python implementation, converting an Excel column title into its corresponding column number. Key differences include Java's explicit type declarations, use of the charAdd method to access characters in a string, and the lack of Python's ORD function, which is replaced by directly subtracting a from the character. The algorithm iteratively computes the result using base 26 arithmetic. The problem Excel sheet column number involves converting a column title, such as those used in Excel, into its corresponding column number. This is essentially a base 26 number system conversion, where each letter represents a value, A corresponds to 1, B to 2, and so on until Z, which represents 26. For multi-letter titles like AA or AB, the title is interpreted as a sequence of digits in base 26, similar to how we interpret decimal numbers. The Python solution provided uses a straightforward approach to solve this. It iterates through each character of the given title, converts it into its numerical value, and accumulates the result by multiplying the current value by 26 and adding the character's contribution. We'll now step through this logic using some examples to understand how the solution works in practice. To begin, let's consider the simplest example, where the input column title is a. First, we initialize the variable result to 0. Then, we loop through the string column title, which in this case contains just one character, a. The character it is converted into its numerical value by calculating ORD plus 1, which evaluates to 1. Next, we update the result by multiplying it by 26 and adding this value. Since the initial result is 0, the computation becomes result equals 0 asterisk 26 plus 1, resulting in result equals 1. Since there are no more characters in the string, the loop exits, and the final output is 1. This demonstrates how single character titles are directly mapped to their corresponding numerical values. Now, let's look at a more complex example where the column title is AB. Again, we start by initializing result to 0. The first character we encounter is a. Its numerical value is computed as ORD plus 1 equals 1. We update the result using the formula result equals result asterisk 26 plus 1, which gives result equals 0 asterisk 26 plus 1 equals 1. Next, we move to the second character, B. Its numerical value is calculated as ORD plus 1 equals 2. Updating the result again, we compute result equals result asterisk 26 plus 2, which evaluates to result is equal to 1 times 26 plus 2 equals 28. With no more characters left in the title, the loop ends, and the final output is 28. This example shows how the algorithm processes multi-character titles by treating them as a sequence of base 26 digits. For the third example, the column title is ZY. We begin by initializing result to 0. The first character is Z, which is converted into its numerical value using ORD plus 1 equals 26. We then update result as result equals result asterisk 26 plus 26, resulting in result equals 0 asterisk 26 plus 26 equals 26. Next, we process the second character, Y. Its numerical value is computed as ORD plus 1 equals 25. Updating the result again, we calculate result equals result asterisk 26 plus 25, which becomes result is equal to 26 times 26 plus 25 equals 701. At this point, all characters in the title have been processed, and the final output is 701. This example highlights how the algorithm handles titles with higher numerical values by continuing to shift and add contributions from each character. The algorithm is efficient because it processes each character in the column title exactly once, resulting in a time complexity of O(n), where n is the length of the title. Additionally, it uses only a constant amount of extra space, giving it a space complexity of O(1). This efficiency makes the solution well suited for handling even long column titles. By interpreting the title as a base 26 number and updating the result iteratively, the algorithm ensures correctness while maintaining simplicity and optimal performance. To analyze the time complexity of our solution for the Excel sheet column number problem, let's start by breaking down the operations involved. First, the function iterates through each character in the input string column title, which has a length of n. This results in a loop that runs exactly n times. Next, during each iteration, we use the ord char function to convert the character into its corresponding ASCII value. This operation is constant time, or O1. Finally, we perform arithmetic operations, specifically multiplication, addition, and subtraction, to update the result with the formula result equals result asterisk 26 plus, ord char, ord a, plus 1. Each of these operations also takes O1 time. Since the loop runs n times and each iteration involves a constant amount of work, the total time complexity of the solution is O(n). Now, let's examine the space complexity of the solution. The input string column title is passed to the function, but since it is read-only, it does not contribute to additional memory usage. The solution uses a single variable, result, to store the cumulative sum as we process the input. This variable requires a fixed amount of memory, or O1, space. Importantly, the solution does not use any additional data structures like arrays or dictionaries, which means no extra memory is allocated. Therefore, the overall space complexity of this solution is O1, as it remains constant regardless of the size of the input. When comparing this solution to a brute force approach, the optimization becomes clear. A naive method might involve generating all possible column titles up to the given one and counting them to determine the corresponding number. However, this approach would be extremely inefficient, with a time complexity of O(26 to the power of n, where n is the length of the string, due to the exponential growth in the number of possible column titles. In contrast, the optimized solution directly computes the number using a base 26 positional system, eliminating the need to generate intermediate titles. This reduces the time complexity to O(n), and the space complexity to O1. Mathematically, this is justified because the algorithm processes each character exactly once, performing constant time work per character, and uses a fixed amount of memory throughout. Finally, let's consider the best, average, and worst-case scenarios for this algorithm. In all cases, the time complexity remains O(n), because the number of iterations depends solely on the length of the input string column title. The specific values of the characters within the string do not affect the number of iterations. Similarly, the space complexity remains O1 across all scenarios, as the memory usage does not depend on the input size. In conclusion, this solution is highly efficient, achieving optimal performance with a time complexity of O(n) and a space complexity of O1. This makes it well suited for converting Excel column titles to their corresponding numbers in a straightforward and resource-efficient manner. When solving this problem, there are a few common mistakes to watch out for. First, let's talk about the incorrect calculation of positional values. This often happens because column numbers in spreadsheets are based on a one-indexed system, not zero-indexed like most programming environments. Forgetting this can lead to off-by-one errors, especially for multi-character strings like AA or ZZ. The fix is straightforward. Make sure you adjust for the one-based indexing by adding or subtracting one where necessary in your calculations. Another mistake is using nested loops to convert characters to numerical values. While this might seem like a simple approach, it's inefficient. Each iteration adds unnecessary complexity, turning what should be an O(n) solution into O(n squared). Instead, use direct arithmetic, subtract the ASCII value of a from the character and add 1 to get its position. Lastly, overlooking edge cases can trip you up. Strings like a, Z, AA, or ZZ, as well as very long column names, can reveal issues like off-by-one or overflow errors. To avoid this, make sure you explicitly test these boundaries during development. Now, let's address some additional mistakes that can impact your solution. One is not handling large inputs efficiently. It's easy to assume that input strings will always be small, but in interviews or real-world scenarios, you need to account for scalability. Extremely long strings can overload a poorly optimized solution, causing it to exceed time limits. To fix this, aim for a solution that processes each character in a single pass with minimal operations. Another issue arises when the problem statement is misinterpreted. For example, some might confuse column numbers with indices or misunderstand how letters map to numbers. This can lead to fundamental logic errors. The best way to avoid this is by carefully reading the problem and clarifying any assumptions. If this is an interview setting, don't hesitate to confirm your understanding with the interviewer before jumping into the solution. Understanding the broader context of this problem can also give you an edge. Fundamentally, this is a variation of base conversion, in this case, converting from a base 26 system. Recognizing this pattern makes it easier to generalize the solution to similar problems in the future. Scalability is another key consideration. During interviews, always assume the possibility of edge cases with large inputs unless explicitly told otherwise. An solution should be your goal to handle these efficiently. Additionally, it's important to communicate your thought process clearly. For example, explain why you're subtracting and adding 1 to calculate the column number. This shows that you understand the one-based indexing system and can articulate your reasoning. If you're looking for a helpful analogy, think of this problem in the context of Excel spreadsheets. This can make the logic more intuitive and relatable when explaining it during interviews. This problem also has connections to several related challenges, which can be useful for practice. One example is LeetCode problem number 168, the reverse of this problem, where you convert a column number back into its corresponding title. Then, of course, there's problem number 171, the exact problem we're discussing here. Another related problem is number 13, Roman to integer, which involves mapping characters to numerical values and summing them, similar to this problem. Finally, number 38, count and say, emphasizes string manipulation and identifying patterns, skills that can also help here. As for alternative approaches, the iterative method is the optimal choice. It's simple, efficient, and runs in O(n) time complexity, directly processing each character. A recursive approach is another option, but it's less efficient and harder to implement for large inputs, so it's best avoided unless explicitly required. Lastly, a pre-computed lookup table could work if the mappings are reused multiple times, though it does require extra space. Each approach has its trade-offs, so pick the one that suits the scenario you're working in. Great work! We've successfully solved the Excel sheet column number problem and explored its key concepts. Remember, practicing problems like this helps build strong fundamentals in string manipulation and numeral systems. Thanks for tuning in, and don't forget to stay curious and keep coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!